Well, I didn't show this slide in the earlier lecture. This is where we now find ourselves. Well, up until today, we had focused on this bottom part of our decision tree. You can see the key point up here at which we entered into all of this descriptive and inferential statistical methodology here, all these methods, was this point here, and that is that we had interval or ratio data and we wanted to do something with it. And what has followed from there is from summary, data summary, all the way through into hypothesis testing, and we've wrapped up with that on in last week, at least from the point of view of categorical variables on the x-axis and a continuous variable on the y, with the ANOVA. We still have another one out here to fill in. But before we get to that, because the ANOVA bears many similarities with another analysis technique, before we get to that, we're focused on a completely different pathway. A pathway that uses nominal or ordinal data to compare frequencies. And in particular, we're using the chi-squared approach. Now, there are many other approaches that sit up the top here. And next week, I'll highlight some of those approaches in the second lecture for week 12, just to open your eyes to the analogous set of analyses that are, well, analogous to these down the bottom of the slide. There's a whole family of analyses up here that make use of nominal and ordinal data. We'll come to those in a little bit. In the lecture today, earlier today, I covered the basic idea around a chi-square analysis in which we analyse frequencies and compare a set of expected frequencies to observed frequencies. Now, at the end of the lecture, I highlighted that while our comparisons of a data distribution to a null or a completely random distribution is interesting in some respects, it's also a fairly weak comparison. You saw earlier today our diameter distribution and how obviously non-random that distribution was. There was a very strong tendency for diameters to concentrate towards the smallest end of the diameter range and very few in the upper end. Now, comparing a distribution like that to a completely random distribution seems a little redundant, and in some respects this is the kind of test that's often referred to as a straw man hypothesis, where our hypothesis is almost intentionally so weak that any data, for that matter, anything, could knock it over and lead us to reject or find evidence to reject H0. Well, that's indeed a weakness in this case, but we do not necessarily need to assume a completely random distribution. There are many other distributions that we can assume that we can use to analyse environmental or biological data. And here are just a few of those. Now, we're not going to go through these in any great detail, but be mindful that these distributions, binomial, Poisson, negative binomial, and these later down the bottom here, especially this one here, the gamma distribution and the log normal, are very valuable. I'm just going to mute you there. Valuable in comparing our data distributions. And in the lecture, I highlighted the log normal distribution that is one that is often used to describe the underlying distribution of size-based data, things like diameter or even mass data. Also, distributions like the gamma distribution are useful for looking at size, but also spatial data too. Up the top here, we have this one referred to as the Poisson distribution. The Poisson distribution is a useful one for analysing the occurrence of outcomes in space or in time. So you can see that any number of distributions might be used in place of the random distribution. And it is something that we make use of in an advanced modelling approach referred to as the generalised linear model. Now, in this course, we won't cover, and we certainly don't even attempt to cover, anything associated with linear modelling. We don't cover regression that you might be familiar with from college, from school, and we certainly don't move past correlation, which we'll look at next week. One thing we certainly don't consider is generalised linear modelling. However, in ENVS 2002, if you're interested in taking the next step into quantitative analysis, we do begin working with these distributions. Rather than the uniform distribution, we start working with Poisson distributions, for example, when we start modelling the likely presence or absence of attributes, perhaps dieback, perhaps species presence, anything for that matter. That is something that we take on in ENVS 2002, but it is useful at this point to appreciate that basic comparisons of distributions can draw upon any number of distributions based upon the underlying theory or the biological attributes of the system that we are working with. Those biological attributes may have been defined earlier in earlier studies. So we have other distributions that we can compare to. But these are not the only distributions we can compare to. We can compare our observed frequencies to an expected set of frequencies for the population that we have actually surveyed. Now, how can we do that? Doesn't that imply that we already have data associated with the population of interest? Well, yes, that is true. But the instance in which we undertake a comparison of a set of observed frequencies to a population level set of frequencies is when we are comparing two levels within the same population. Now, earlier in the earlier lecture, we saw an example of how a circumstance like that might arise. At the start of the first lecture in this week, I highlighted these data in which I used our diameter data from Black Mountain to generate frequency histograms. Now, in this case, they're not the histograms that you are perhaps familiar with. They don't use bars, but rather, like Pook and Moore, I created my frequency diagram as a line. And that lets me see the shape of the distribution. Now, remember what I highlighted at the start of the first lecture today, this huge difference, not necessarily in the raw frequencies themselves, yes, there's that difference, but this big difference in the shape of the distributions. See how Eucalyptus rossii, for example, on north aspects, has a large number of very small diameter trees that progressively decline, or quite sharply decline, and then stay very low into the larger diameters. That's a little different to Eucalyptus macrorinca. You can see that that species distribution starts below 5%, climbs, and then turns and comes back down again. So there are differences in the shape of these distributions aside from the differences in the raw numbers. Now, that difference in shape can be useful when it comes to interpreting the impact of, as I mentioned in the earlier lecture, the impact of disturbance, for example, on ecosystems, be it an ecosystem of trees or anything else. To undertake an analysis of data like this, we undertake something that we refer to as a contingency analysis, in which we compare the frequencies across our factor levels. Now, here I have two factor levels. I have a factor level for Eucalyptus macrorinca, and I have another one for Eucalyptus rossii. It doesn't have to be just two. We could have all of the species on Black Mountain if we wished, and we could analyse their frequencies simultaneously relative to each other. In a way, it's very much like the ANOVA, where we have multiple levels and we are looking at deviation away from a common overall mean in the ANOVA, in a contingency analysis, we look at deviation away within each level, deviation away from the common distribution. That is, the distribution that is made up of both species here at the same time. We compare that to the distribution of each species one at a time. And that's how we undertake a contingency analysis. Now, this is a contingency table, and while it looks perhaps a little bamboozling, a contingency table is really very straightforward. It's really just a set of summaries of frequencies, both absolute frequencies and relative frequencies in terms of percents. The summary here, there are so many rows within each cell because the data summary happens in two different directions: across the rows, down the columns, and then for the entire data set. And of course, as you can see up here in the top right hand corner, there are additional metrics as well. So we can choose to present all sorts of things in a contingency table. But using JMP, what I've done here is I've chosen to represent the key elements that go into creating a chi-square for a contingency-based analysis of diameter classes across species on a south aspect. So again, across diameter classes from 10 through to 80 there, for two different species, two separate sets of rows for those two different species, and of course it's just on south. Now we'd have to do the analysis again separately for north. Alright, so what do we have in here? We have a list of what we find in each of these cells. The total count of observations that are sitting in each cell. Why don't we bring that up? The total count, the absolute frequency, if you like, of the number of individual Eucalyptus rossii that fall within a 10 centimetre class, 20 centimetre, 30 and so on. You can see exactly what we saw in our graph, that we have many observations over here in the smallest diameter class, and then it declines as we move up. In addition to that, we have absolute frequencies represented across columns. So while we had that highlighted section going across the row, now we have, for our 10 centimetre class, you can see that we have 137, 110, and then 247 down the bottom as the total. So we are summing both across, you can see here the sum across the row, and a sum down in the columns. Now that might be obvious, but it's important that we observe that those row and column marginal totals are there, because those row and column marginal totals, the 403 over here and the 247 down there, they become the basis for calculating our expected values within each cell. That is, if we have 403 observations across this row, and down this row, down this column, we have 247, we should then see a proportionate distribution of observations across both of these two sets of data, across these two species. So our general pattern in the two distributions for each species should follow the same pattern that we see here in a relative sense, and though the absolute values should reflect the difference between how many of each species we have within our data set. So we have a relative expression and our absolute expression as well. Alright, so we have our absolute frequencies. The table as well is made up of percentage-based frequencies. Here you can see the percentage of observations within the row. So as we go along the row, we get to the end and you can see 38 just over 38%, nearly 39% of all of the observations in the data set are for Eucalyptus rossii. The remaining 61% on a south aspect are in Eucalyptus macrorhyncha. And then within this 38.8%, you can see where the individual percentages fall across the different diameter classes. So this is expressed, so the percentage frequencies here are expressed in terms of the total data set, where the frequencies lie within the total data set. The next one down reflects the percentage of observations for the 10 centimetre diameter class that falls within each species, and then the next one down again represents the percentage falling within each of these diameter classes just for Eucalyptus rossii. So there are different directions that the contingency table is summarising. So the next one down, not normally reported in a contingency table. Normally these last few columns are not included, and in many cases one or two of these other ones are not included. But I've chosen to add them in so that we can see the calculation process. I'm not going to step through it by hand because it's just too dull to step through it by hand, although a contingency table is something that you can calculate relatively easily. Here we have our expected value. Our expected value for the frequency of 10 centimetre diameter classes trees within Eucalyptus rossii. Remember, this frequency needs to reflect the number of individuals that we measured in Eucalyptus rossii and the respective frequency across the diameter classes for both species simultaneously, so for the entire population. Our null circumstance here is that the distribution across Eucalyptus rossii and Eucalyptus macrorhyncha are the same. So using our row and column marginal totals, column marginal total and row marginal totals, so the column marginal total down here and the row up there, divided by the grand total. So we multiply these two by each other, divide them by their grand total, and we see here, and that generates for us an expected value for each cell. So you can see as we move along, we would use a different column total, or if we moved down to the other species, we'd make use of a different row marginal total. The assumption here is that, again, these two species across their diameter classes have the same relative distribution given to us by the underlying population distribution for both species at the same time. Right, so each cell within our contingency table receives an expected value. Of course, if there's an expected value in there and an observed value, that means that we can calculate a chi-square value for each cell, and that's what we have just here. A chi-square value, the same calculation again as I mentioned in the lecture, where we calculate the difference between our observation, the number observed, minus the expected values that we've just calculated, squared divided by the expected. So that's exactly the same calculation that I highlighted in the lecture earlier today. And then we sum our chi-square for each cell. We sum together for the columns, and we sum our two columns across all of the rows. So we end up with a sum of all of our 1, 2, 3, 4, 5, 6, 7, 8, 16 cells. Gives us a total chi-square value. We then have our final chi-square value, and we test that chi-square value against a critical value. I also mentioned this in the lecture this morning, where our H naught, again, is that our chi-square critical is greater than our chi-square calculated. So exactly the same H naught, or structure to our H naught, that we've used for the ANOVA and for our t-tests. Now, how do we arrive at our chi-critical? Well, we make use, again, of the same alpha level, 0.05. But in this case, you'll remember this morning I mentioned that the degrees of freedom are represented by k minus 1. So what do we do here? Bearing in mind that in the morning's lecture, k was the number of categories within our diamond class. What do we do now? Well, we do exactly the same thing, but we need to have k diamond classes as well as across, two species. So we have our row degrees of freedom and our column degrees of freedom. Row minus 1 times our column minus 1 gives us our total degrees of freedom. So our degrees of freedom here, we start with 16 cells, and gives us 7 degrees of freedom. And then we compare to a chi-square table. Now, what does the chi-square table look like? Now, let's just open it up. It's open on the Waddle side, but I've already got it open here, so I'm just going to move it across. There's our statistical tables for the course, and if I grab the toggle, go all the way down to the bottom, you'll see that down the bottom here we have a table of critical values for chi. You can see our degrees of freedom down on this side. We had a set of degrees of freedom there. We had 7 degrees of freedom, and we just read across to our 0.05. So we have a chi critical of 14.1, and we just compare our chi calculated to that value. But just as we've done in our other tests so far, we can also calculate a probability associated with our chi calculated. Now in week 12, you're going to undertake that very thing for your Ogma-Graptis data. We're going to test Cook and Edwards' idea around the distribution of scribbles on trees. Not only are we going to test whether there is a difference in the distribution of scribbles on trees relative to the assumed direction, but we're going to compare our distribution to Cook and Edwards. And we're also going to consider, because Cook and Edwards suggested that wind direction played an important role in determining where scribbles, or could play an important role in determining where scribbles were located on a tree, we're going to compare our data to data that represents the typical wind directions on Gallibarry Black Mountain. Now, of course, that means that I'm not going to analyse Ogma-Graptis data here, but we do need some data that we can analyse as an example of how a chi-square might work. Now remember that chi-square is applicable to survey data just as it is survey data of people. So outcomes from questions based upon, say, questions based upon people's preferences or opinions from a question. So a good example then might draw upon people's responses to a questionnaire. And one of my favourite questionnaires, one that was published some time ago online, is this one. A questionnaire that asks perhaps one of the most important questions of all. Which Radiohead album is the greatest? It's like 1995 all over again. Now, from my point of view, one album is always going to be the best. This one that's playing right now. This album was released in 1995, and if you don't know it, it's the Bends. And if you don't know who Radiohead are, well, you know, whatever. But from my point of view, this album has particular values that none of their subsequent work has. Now, that may be a product of my age, but it does beg the question of whether there is a difference in people's preferences for different Radiohead albums. And The Guardian asked that question some time ago, and the results were published online. Now, this is a bit loud. Now, perhaps unsurprisingly, this album was selected more frequently than anything else. You can see the results presented just here. The album that's playing behind me, the opening track for it anyway, is for OK Computer. So after a few releases, Pablo Honey and the Bends of course had the band's massive hit Creep on it. After that album, Radiohead became immediately recognisable to many people around the world, and this release, OK Computer, was very, very well regarded, and you can see it was regarded by many people as the greatest of their albums. Now, we can analyse whether there is a pattern to the Radiohead album preferences by comparing it to an assumed distribution of there being no preferences at all. Now, again, that comparison might sound a bit foolish given how obvious the difference is between our data here and what would be a null distribution in which all albums were equally selected. But, you know, it's a good place to start as an example. So we can ask this question: is there really a difference in preference for Radiohead albums? Does the observed set of preferences reported by The Guardian, does that observed set of preferences actually reflect an underlying difference in preferences, or does it just approximate a random distribution? Okay, so we have that question. Are the apparent preferences different, or do they differ from what we would expect by chance? So do they differ from what we would expect within each category, that is for each album? How do we calculate our expectations? Well, remember from the lecture this morning. What are our expectations? Well, under the null proportional model, and that's what it's referred to, the proportional model, where every frequency is proportional to the number of observations in the data set. What it allows us is to come up with a set of proportions or frequencies that are free of any information around Radiohead albums and people's preferences or album sales, anything that might give us some guidance to what people regard was the greatest album. So this is an approach, as weak as it may be, this is an approach that we use when we are working with a set of data, well, that we have absolutely no expectations about. So if we assume we know nothing about Radiohead or their albums or people's preferences for them, we can compare to the proportional model. That is, there is no album preference whatsoever, so people don't select one category over another, and all albums are rated equally. Now, both of those things are probably untrue, but these are the assumptions that we start with for the proportional model, that all categories are equal and there is no preference, that the selection is directly proportional to the number of observations and categories within the dataset. As I covered in the lecture, we calculate our expected values for each category, in this case albums, each category based upon 1 over k. What is our k in this case? Well, within the Guardian survey, bearing in mind it was conducted some years ago when Radiohead had only released 8 albums, you can see that the 8 albums are listed here, and each of them are assigned an equal probability of choice. That is 1 on 8. Each has a 0.125 proportionate likelihood of being selected. Our next question then is how these expectations compare to our observations. Well, here are our observed frequencies based upon the Guardian dataset. So if we just go back to the Guardian dataset for a moment, you can see their observed frequencies here, and I've just inserted those into this table. So we have our expected frequencies and our observed. Now bear in mind that the calculation for chi-square is not based upon the frequencies in terms of their relative frequency themselves, but rather we need to calculate the expected number and compare that to the actual number of outcomes. But before we get to that, let's just recognise, first of all, that our H0 here is that the proportion of the data set or the proportion of respondents that select Pablo Honey is equal to what we expect, as is the case for the Benz, OK Computer, and the remaining albums here down to King of Limbs. So we have those expectations, that H0 based around our observations and expectations, and our calculation method follows the observed minus expected squared on the expected, all summed across all albums. Again, let's also remember the shape of the distribution that we're working with that I mentioned in the lecture earlier. That is, the chi-square distribution changes its shape depending upon the number of categories we're analysing. You can see with a very small number of categories, we expect there to be a large number of outcomes where the chi-square values are very small. Very small differences, yes, maybe, but there are few calculations to make, few combinations that we are calculating a chi-square for and then summing. Remember, here is our H0. Okay, so on to our data. So we have a set of expectations and a set of observations. If we just generate the data, it was a little bit difficult to come by, so we had to sort of auto-generate some. We might expect 12.5 people to select each album, and then we have the respective observations themselves. And we calculate our chi-square from our observed minus expected squared divided by our expected. It gives us a column of chi-squares. And we then sum those chi-squares, and so what are we left with? Well, we're left with a very large chi-square value. Is that a significant outcome? Well, let's test it relative to our chi-critical. 1, 2, 3, 4, 5, 6, 7, 8 albums. That gives us 7 degrees of freedom. We already looked at the chi-square table and we saw that the chi-critical was 14.1. So in terms of rejecting or accepting, here we have evidence to reject H0 because our chi calculated is larger than our chi critical. Now, does JMP do all of this for us? Well, yes, it does. So why don't we have a look at that? Well, it just so happens, of course, that I, somewhat after putting these lecture slides together, managed to access the Guardian data, which actually was more complicated had a little more detail than I originally thought. You can see, let me move it over, the Radiohead data actually included some demographic information about the people who had responded. And there are 1,200 respondents. I think they must have capped it at 1,200 respondents in total. So here we can analyse preferences across albums. So you can see the album that the participant selected. You can see here I've coded when the album was produced. We'll think about that in a moment. And you can see the decade of the year in which the person who responded was born. That's something else that might prove useful in a little bit. But first, let's just have a look at the data and how we might analyse this. Well, analysing frequency data in JMP is just as easy as it has been all the way along when we have a single variable to analyse. We just use the Analyse Distribution option. And once we're there, we just need to select our categorical variable that we want to analyse and look at the frequency of. Select that, put that into Y columns, and here is that frequency histogram indicating the number of times each album was selected. You can see that OK Computer had 324 respondents. Now, how do we run a chi-square in JMP? Well, it couldn't be too much more straightforward, really. The little red arrow down there next to album, the name of the categorical variable that we're testing, and we test the probabilities. Now, down the bottom here, we now have to insert something to tell JMP what our hypothesized probability is for each category. Now, we could put in here 0.125, that is our 1 on k for each category. Alternatively, we don't really need to do that. What we can do in JMP is just put any number we like in each of these cells, so long as each of these numbers is the same. So if I just put 1 in every one of these little cells and leave this little toggle here ticked that says fixed hypothesized values, what's going to happen is that JMP will count the number of categories, generate a 1 on k for each of these categories, and multiply it by our hypothesized probability in here. And if it's 1 in every single category, then it's going to give every one of our categories the same proportionate frequency. So I can just press done here, and JMP corrects what I've entered so that they're all equal. You can see they're all 0.125. Now, JMP has calculated 2 sets of chi-square values. The one that we in particular are interested in is not this log likelihood. That is a piece of calculation that we cover in ENVS 2002, the log likelihood. Rather, here is Pearson's chi-square. Pearson's chi-square is the chi-square formula that we've covered so far in the lecture content. And you can see here that in this case we have 769 as a chi-square value. That is huge for our 7 degrees of freedom. So huge that you can see the associated p-value here of less than 0.0001. That's less than 1 chance in 10,000 that H0 is true given our data. That is, there is a distinct album preference for different Radiohead albums. Now, you'd have to really have a very, very poor interpretation of data not to have already inferred that from what you can see in front of you. And that goes to the point that I made earlier today, that when we compare obviously non-random distributions or assess non-random distributions on the basis of a simple proportional model, the outcomes are not surprising and at times not necessarily all that informative. Now, can we undertake an analysis that is a tiny bit more informative? Well, to do that, we need to bring together our statistical and our context-based knowledge. Of course, if you don't know anything about Radiohead, then you might not be able to do that. After a long semester, listening to some Radiohead is relaxing. What we need to do when we're looking at data all the time, but when we're looking at analyses like this, we need to think very, very carefully about how the survey was designed before we get headlong into interpreting the results. Now, what are the elements in this survey that we need to bear in mind? You can see I'm taking my time because it's a great song. Using 3/4 time. All right, 5/4. Okay, so our characteristics. First, we need to think about a number of things associated with a survey. What the characteristics of the underlying population that have been surveyed are. Is the sample a self-selecting set? And are they fully informed when it comes to all of the options in the survey? Well, why are these three things important? Well, consider how much experience you might have had with Radiohead up until this moment. Maybe they're the last band you'd think about on a daily basis, whereas for me, I listen to them every day. So maybe within the population that's surveyed, maybe attributes like age are an important element when it comes to understanding Radiohead preferences. Maybe people who responded to the survey, just like people who respond to surveys all the time, were self-selecting. And maybe within that population too, there is a difference in terms of the experience of Radiohead. Someone my age has experience with Radiohead all the way through their career or their recording career, whereas someone younger, maybe your age, has less experience of that. So the comparisons, well, we might need to be more careful about them because underlying attributes of the population of people we've surveyed can confound what we're finding. We also need to be careful here. Fortunately, in our case, every single album here is a distinct album on its own, associated with a different recording period. Or is it? 2 albums that are in this group of albums we're analysing were produced during the same studio sessions and in some respects are regarded as part 1 and part 2 of the same release. So is it appropriate for us to compare those 2 albums as standalone cases? We have to think carefully about these things. Now, I'm not going to change my analysis based upon that, but when we're presented with survey data, these are the things that we need to think carefully about. Not thinking about Radiohead albums, think about the categorisation and the population. Now, when we think about Radiohead albums and divisions between fans, there's no bigger division between preferences for OK Computer and for Kid A. Quite a large portion of the Radiohead album, of Radiohead's fan base, was split when Kid A was released. It was a substantial departure from the more rock-oriented sort of releases prior to Kid A. And there are, within the survey run by The Guardian, these kind of comments about Kid A and albums afterwards, suggesting that there is a distinct difference in the preference for albums released prior to or following the year 2000, the year in which afterwards, anyway, that Kid A was released. Now, we can analyse that within our data. As you saw previously, I've split the albums based upon when they were released. So we can analyse based upon albums, but we can also lump the categories together and analyse it separately. So we can compare pre-2000s to post-2000s. So let's do that. Let's go back to JMP and compare, instead of album, let's compare the album when it was released. Again, we go into distribution, not decade of birth, album released, into our distribution, and analyze using test probabilities. Again, I'm going to put in 1 and press done. Now, despite the fact that there is only a small difference between our proportionate frequencies, the very large number of observations here indicates that yes, there is a distinct difference in album preferences between pre and post 2000s. Many more, well, there are a few more preferences towards post 2000, and that outcome is significant. Now, why might that be? We need to give some more consideration to our data set. Is it actually that more people prefer those albums, or is there an underlying difference associated with the age and the number of people in each who have opted to select each album? So here's some summary of our respective calculations. You can see based upon what we just saw a moment ago that we accept that we have evidence to reject H0. Now, let's think about the problems associated potentially with the survey. Now, when I think about this survey and I think about Radiohead, I'm presented with one clear interpretation. And that is when I listen to this album in particular, I'm reminded of when I was in your position as an undergraduate, and all the experiences, all the relationships that I had during that period that informed my love of music, and I think about when I listen to music from that period. Indeed, this is one of them. So it may be that because by virtue of my age, I am particularly associated or have strong association with one album. So if age is a determinant, then we need to be careful about whether our interpretations reflect the age of the respondents or actual preferences for albums across the population. That is a question we always need to ask of data. We need to look for potential confounding influences that have generated the effects that we are witnessing. In this case, are music preferences age dependent? For all the reasons that we can see here. Is it because of personal experience? Is it nothing to do with that at all? Or is it just the age profile of the Guardian readership? Or maybe people who were born in the 70s just have much, much better taste in music than people who were born afterwards. Who knows? We also need to be careful about the way that the surveys have categorised respondents. Surveys generally also, in addition to the responses themselves, draw demographic data. And those demographic data allow us to control for confounding effects. And contingency tables are the basis for analysing frequency data based upon demographic factors. The other possibilities around confounding factors is, well, can we really regard each album as equal? Was there equal opportunity to select perhaps in rainbows. If you're not aware of in rainbows was released online. So it's a pretty antiquated idea now, but it was released online and you were allowed to pay whatever you wanted for it. It suddenly became very popular. Some people were paying $1 for it and others paying the full price of an album. And of course it became very popular as a consequence. So can we really compare that to an album that people had to pay full price for? What about this issue of independence? OK Computer was a massive hit. They sold many, many, many albums and Kid A followed immediately afterwards. Is the popularity of Kid A a consequence of the popularity of OK Computer that came before it? So is there a time-related effect? Can we say that the preferences for Kid A is independent to how popular OK Computer was? How do we analyse that? How do we handle these things? We need to look for these attributes within data sets. And then the sample itself. Who has time for online surveys? Not me.